Thank you for tuning in. The topic of this video is going to be selected area diffraction, and specifically what is selected area diffraction and how do we record selected area diffraction patterns. If you haven't already done so, you should go watch the video on basic operation of the instrument. I'll put a link in the description box below. But I recommend that you would watch that first before watching this video if you haven't already done so. So I have already pulled up here a live image of our test specimen, and I'm going to go ahead here, increase the exposure time. Okay, so that is the image here, or the image of the specimen. This is a bright field image, again meaning I've only selected the direct beam with the objective aperture. These lines are drawn here just to indicate the middle of the image, and actually that's useful for when we're doing the diffraction pattern collection, which we'll get into in a minute. But I'm going to go ahead and do an acquire here so we can see this a little bit more clearly. Okay, so what you see here are basically two regions. So you have this dark region, which is a single crystal silicon substrate, and I've aligned it to the 110 zone axis. Okay, so in other words, that is the crystallographic direction that's coming out of the page. And then this here is a film of aluminum nitride that has been grown on top of the substrate. So the basic question then, which is the topic of the video, is what do the diffraction patterns look like, okay, for these two regions? Okay, so what's the diffraction pattern look like from the silicon? What's it look like from the aluminum nitride? Okay, so I'm going to go ahead and just minimize this. Actually, I'm going to tweak with the focus here really quick because it is a little out of focus. It's a little better. Okay. Okay, so again, the question is, we know that we can get diffraction, a diffraction pattern in the specimen, because we did talk about diffraction mode in the general operation video. So the question now is, what's the diffraction pattern from here? What's the diffraction pattern from here? So I'm going to come back over here to the viewing screen. Okay. And now one thing I'm not going to do, okay, I'm not going to push the diffraction pattern or the diffraction button and put a diffraction pattern up here, okay? And the reason for that is I'm probably going to destroy my camera scintillator if I do that. Okay, so right now I'm using beam conditions, so we see spot size 1. I'm using really high current beam conditions which are great for imaging. They're not really good for recording diffraction patterns because, most importantly, you're probably going to damage the camera. Okay, so we'll talk about how to set up the instrument for recording the diffraction pattern in a minute. Okay, but anyways, I'm going to flip the screen back down here. Okay, and then I'm going to go into diffraction mode. Okay, again, hit that diffraction button. Okay, and I can't really see anything because I've got my objective aperture in, so I'm going to take it out. Again, there's the objective aperture. Okay, and now it's out. So now you can see the diffraction pattern. I'm going to go ahead and increase the camera length here. Okay, and we'll go a little bit more. We'll see if we can get that a little bit better. Okay, a little bit better focused. Okay, so now what we're seeing here is a diffraction pattern that is representative of basically the whole area that's being illuminated by the beam. So if I come back and I go back into image mode, okay, so that's where I'm illuminating. It's a little hard to see, but basically that's bigger than this whole area. Okay, so in other words, my diffraction pattern, I'm getting contributions from this region and this region. Okay, and that's generally not useful when you're trying to isolate what you're getting from one area versus another. Okay, so this is where the concept of selected area diffraction comes in. So if I come back here, okay, if I come back here, what you actually see, and it's probably a little bit hard to see this, okay, but I actually see two sets of spots. Okay, I see a set of spots that's from the substrate, and I see a set of spots that's from the film. Okay, and I'm seeing both of those simultaneously. So now the question is, how do we isolate one from the other? And that's where selected area diffraction comes in. Okay, so if I come back, okay, I come back into image mode. I don't have my objective aperture in, but I'm going to pull the image back up on the camera right here. Okay, I don't have the same contrast, obviously, because I don't have an objective aperture in. But what I'm going to do now is I'm going to use an objective aperture to define my area that's contributing to the diffraction pattern. So that's what a selected area aperture does. It selects an area to contribute to the diffraction pattern. It's sometimes also referred to as a field limiting aperture because, again, it limits the field that contributes to the diffraction pattern. So this is the selected area aperture right here. This has 4 different settings. It works a little differently than the other aperture strips, okay, because it has an in-out flip bar here. So 4 is the biggest, 3, 2, and 1. 1 is the smallest. So if I flip this from out to in, and I come back here to the image, okay, you can see what's happened. So now I have an aperture placed in the image plane of my objective lens. So I'm only, right, seeing that selected area, okay, hence the term selected area aperture. And I can position this, again, using this knob and this knob. I can position this wherever I want. Okay, so if I put it over the silicon, right, you can see I'm only over the silicon right now. If I move this over here, now I'm basically right in the middle. Okay, I'm on that interface between the two. And if I go over more, okay, now I'm just over the film. So let's start by just looking at this. Okay, so we're just looking here, we're right over the silicon. Again, I'm going to put the screen down, and I'm going to go back into diffraction mode. Okay, and actually, it's a little hard to see, so I'm going to pause this and turn off the lights because I did lose some signal. We'll get into that in a second as well. So, lights have been turned off, and this is probably a little bit hard to see, so you'll notice that I lost intensity in the diffraction pattern, okay, and that's expected, right? So your area that's contributing is less, okay, so you're going to lose current, okay, that reaches the viewing screen, and you're going to lose signal in the pattern, okay. But the important part here is if you look carefully and you compare it back to what I had before, I don't see all the spots that I had before because I'm just over the silicon, okay. So now what I'm going to do, I'm going to go back into image mode here, put my screen back up, and now I'm going to shift my selected area aperture so I'm just over the film. Okay, screen goes back down, go back into diffraction. Okay, and it's probably hard to see, but the pattern looks different now. Okay, again, because I'm over a different region which has a different crystal structure, or maybe it has a different crystallographic alignment. Okay, but again, I'm not seeing what I was seeing in the silicon. Okay, so the aluminum nitride is quartzite. If you're not familiar, the silicon is diamond cubic. They have different crystal structures. Okay, and so that's the idea here. Okay, is I can field limit what contributes to the diffraction pattern. Okay, so the obvious question now is, well, that's great, we can see it on the screen here, but
I want to record it. Okay, and of course I should mention as well, you see right here, okay, that's our indicated camera length. So if I look here, okay, and 1.65 meters is a high camera length. Okay, so higher your camera length, the smaller the angular field of view you see in the pattern, and in other words, your pattern is magnified more. So if I go down, and again, I did cover this in the general operation video, but you can see now I'm down to indicated of 430, and my pattern magnification is smaller. Okay, so this is up to you what you set this at when you record it. Okay, so depending on the structure and what you're trying to see, you may need a short camera length, you may need a longer camera length. Okay, generally speaking though, on this instrument, I like to use either the 430 indicated or the 265 indicated. Those are usually generally good all-around camera lengths, although there are some niche applications where going higher or shorter may be warranted. Okay, so now that we've established that, okay, I'm going to go ahead and cut the video here, and we'll resume it, and I will start discussing how we have to set up the instrument if we actually want to record this pattern with the digital camera and do it in a way that we don't risk causing any damage. So the question now is, how do we set up the instrument so that we can safely record a diffraction pattern with our digital camera? So I should state that the digital camera on this instrument is older. The camera technology has improved greatly over the years, and modern day TEM cameras are capable of taking more abuse, if you will, okay, without being damaged. So abuse in the form of diffraction patterns. Okay, this one can do it too. It's just you have to be a little more careful with it. Okay, so the first place we're going to start with is the spot size. So I'm in the beam tab. So we know again from the general operation video that the lower I go in numerical value of spot size, the more current I have reaching the sample. Okay, and so this is a problem if you're trying to record a diffraction pattern. Okay, so if you're trying to record a pattern with those finely focused spots, and you're putting all that current into a really small area that gets projected onto your camera scintillator, you're going to damage it. Okay, so you can't do this effectively at spot size 1. So you have to go to a higher numerical value of spot size. So this is something that you kind of have to play around with, and we'll go over how to test this, okay, to see if it's sufficient or not. But generally speaking, I'll go up to here between maybe 7 or 8. Okay, so let's start with, for today, we'll go ahead and we'll start with 8. Okay, and leave it there. So if we look here on the screen, okay, and let me do the transition again so you can see that. Okay, this is the image at 8. I'm going to change it from 8 to 1. All right, so again, you're losing a lot of current, okay, when you go up that many settings in the numerical value spot size. But that's what you have to do, okay, if you're going to safely record a pattern with the camera. Okay, so now because I've changed the numerical value of spot size, one thing I need to do at the bare minimum, okay, is I need to reestablish at least the realignment of the C2 aperture, and I should check the condenser astigmatism again. Okay, so I'm going to go ahead and pause the video and resume it after I've done that. Okay, it is a little hard to see, but I can see just here in the room, I can see enough of the beam to do that effectively. Okay, so I'm going to go ahead and pause the video, and I will resume it after I've done that. Okay, so I realigned the C2 aperture, I checked the condenser astigmatism. The condenser astigmatism wasn't really off, but the aperture needed to be realigned, so I did take care of that. Okay, again, you can see what's happened to the image. The beam is there, it is visible, but it is very, very dim. Okay, again, we are at a high numerical value spot size. So now what we have to do is we have to set up the appropriate illumination. So when I say appropriate illumination, when you're collecting selected area diffraction patterns, that's usually being done with what's called parallel illumination, meaning all the electrons, when they are illuminating the sample, they're coming in parallel to the optic axis. Okay, that's called parallel illumination. If we deviate from that, we have what's called a convergent beam, which we're not going to get into in great detail in this video. Okay, but we have to set up the imaging to make sure we have a parallel beam. So the way we do that is with diffraction mode. So if I come back here, okay, again I'm going to go into diffraction, okay, and now I can see the diffraction pattern here. Okay, so I think I covered this in the general operation video, I'm not sure, but the way you have to do this is you take your objective aperture here, it doesn't matter which one, okay, but I like to use a larger one for this because it's going to be easier to see it. So I'm going to put in, we'll go to position 2, okay, and so I can't really see the aperture here, it needs to be shifted a little bit. Okay, so there it is. Okay, so I can see now the aperture rim there. So what I have to do now, and this is hard to do with the camera, okay, but I'm going to look through these binoculars using my focusing screen. Okay, so if I was to look through the binoculars here, right, what I'm going to see is that aperture rim, okay, superimposed on the diffraction pattern. So then what I can do is I can look at the edge of that aperture and assess if it's in focus. So in focus means that it's sharp. Okay, so and this is hard to show just with the camera in my hand here, okay, but it's easy to see looking through the binoculars if that aperture edge is blurry or if it's sharp. Okay, so I'm using the focus knob here, okay, again I'm in diffraction mode, to focus that aperture edge. Okay, so if I do that really quick, okay, excuse me while I just shift the phone off, or the camera off, okay, so just looking at this really quick, yeah, it was basically pretty close, okay, so I made an adjustment, the aperture edge is now focused. Okay, so that's the first part of it. Okay, I'm making sure I'm looking at the back focal plane. What I have to do now is I have to adjust the C2 lens to make sure the beam is parallel. And so the way you tell that is to look at how sharp the spots are. So if the spots are as small as possible, focused, then you have a parallel beam. Okay, so right now it's actually pretty close. So what I'm going to do here, I'm adjusting the C2, which is again, right, that's the intensity knob here on my left-hand panel. Okay, but if you look what happens, okay, you can see now that direct spot, right, that's becoming, okay, you can see what I have now. The spots are broadening, okay, because I don't have a parallel beam. When your spots are enlarged like that, you have a converged beam. Okay, you don't want that when you're doing selected area. Okay, so you want this. Okay, you want the spots as sharp as you can get them, right there. Okay, and again, to make sure this is as precise as possible, you want to look through the binoculars. Okay, I'm going to shift the camera off here really quick just so I can do that. Okay, so I made the adjustment and it's basically set properly. Okay, so now I have a parallel beam. So now what I need to do is take out the objective aperture. And that's important because remember what the objective aperture does. Okay, it limits the portion of the diffraction pattern that ultimately contributes to the image. So if I leave it in, I'm not seeing all of the diffraction pattern. Okay, so I'm going to go ahead, I'm going to take it out now because I don't need it in anymore. Okay, and now I can see, it's probably a little hard to see, but I can see more of the diffraction pattern now. Okay, so I'm going to go ahead and head back into image mode here. Okay, another good question here is what magnification should you use? You want to be in SA mode when you're doing this. I usually go all the way down to the lowest mag, indicated mag in SA mode, which is 6200X. Okay, there's really no benefit to going high with this. Okay, part of the reason for that is it's easy to see the beam when you're bottomed out in magnification like that. But if you go up in mag, the beam gets spread out more over the screen. And remember, you can't adjust. okay, your intensity knob now, because if you do that, you destroy the parallelism. So you can't hands off this guy, okay? So I just bottom it out, okay? Bottom out the magnification while still being in SA mode, okay? So I'm gonna flip up the screen here. Okay, there's the image that we've seen before. Just gonna move it down here a little bit, right there. Okay. Okay, so now you see I have this X drawn on the image. Actually, I'm gonna delete that so I can show you how I drew it. It's not very difficult, but I'm gonna go ahead and delete it so you can see. Okay, the point of that X was to find the middle of the picture rather than to just, you know, ballpark it. So in standard tools here, I've got lines. So you draw one line, whoops, across the diagonal. You draw another the other way. This is a pretty good trick, okay? And then there's your middle, okay? The reason for that is I can use that to center my diffraction pattern, which we're gonna see in a minute here, okay? So I've got my center point marked, okay? The other key that you need to do when you're recording these patterns is to use a beam stop. So what is a beam stop? Well, it's just what it says. It stops the beam or a part of the beam, okay? So it literally is an object that you insert into the image or the diffraction pattern, and it literally blocks off the part of the beam that is illuminating it. Okay, so on this instrument here, it's a little hard to see, but this guy is the beam stop. Okay, so I turn this towards me, okay, and it pulls in. So that's what it looks like right there. Okay, it's got a point on it. There's different designs depending on the microscope, depending on who made it. So yours may not look like this, okay? But then I want to position this, the way I record these, I position this pointy thing right over here. Okay, not the tip, but somewhere in the middle. You want something substantially large right there. Okay, so I'm gonna go ahead. So there's adjustment screws on here. Okay, there's two adjustment screws. There's one here and there's one here. Okay, so I'm making the adjustment here. Okay, so you have right, move it down a little more. It's a little sticky, but that's kind of by design to make sure it doesn't move. Okay, so right there. Okay. So now I've got a beam stop there. What am I going to do now that I have that? So that's going to block the direct beam. The direct beam is the most likely thing to cause damage to your camera scintillator. Okay, and that's usually not what you're interested in anyway when you're recording a selected area pattern. You don't care about the direct beam, you care about the other stuff. Okay, so you really don't want to see that because it may just swamp out everything else, and then you also run a risk of maybe damaging the camera. So we deliberately block it off. Okay, the last part of this now is again the SA aperture. So there's my SA aperture. I flip this, okay, to in, and there it is. Okay, so I can position this however I want. So let's start, we'll put it over the substrate, okay? And again, just over the substrate. Move it back a little bit more maybe. Yeah, somewhere like that, okay? So I'm gonna come back here to the viewing screen, put the screen down, and now I'm gonna go into diffraction mode. Okay, you can't see this, but there is a diffraction pattern there. It's very dim. Okay, it's very dim, which is what you want. Even though it's hard to see, it's very dim. Okay, so I'm actually going to look now through my binoculars here. Okay, I'm going to look now, and I can see, I'll be able to see, it's not easy to see on the phone here, okay, but I can see where my direct beam is, and I can actually move the pattern around. Okay, so in diffraction mode, when you enter diffraction mode, your multifunction knobs are now activated to shift the pattern. And I can actually show you that here with the camera. Okay, so I'm going to go ahead and pause the video for a second. I'm going to then shift the pattern over, and then we'll resume. All right, so I've shifted my pattern over so my direct beam is under the beam stop. Okay, so the only thing left to do now, I've got a live image going. I'm going to put my exposure time back to 0.01. Okay, again, that's for protection, right? The lower your exposure, the less accumulation of charge your scintillator is building up. Okay, the other thing I'm going to do here is I'm going to start acquiring a histogram of the live image. Okay, so on the histogram here, this x-axis, it's a little counterintuitive because this says counts, but this rightmost value here is the max counts that you see here. Okay, so right now you see I'm oscillating between 10 and 20, right? Because I've got no beam on there. Okay, but when I lift up the screen and we see the diffraction pattern, you're going to see that change. So I'm going to go ahead, I'm going to lift up the screen now. Okay, so there you can see the diffraction pattern. Okay, and you can see now I've got some signal there. Okay, and clearly we see the 110 zone axis for a diamond cubic material. Okay, you'll notice that part of the pattern is blocked off. That's again because the beam stop is in there. Okay, so now the question is, we want to do an acquire. What kind of acquire do we need to do? Well, we do a test exposure. Okay, so I'm going to come back here to camera acquire, and I'm going to just do 0.1 seconds. Which probably isn't going to give me something that looks very good. Okay, in fact it isn't, but I can then go to analysis histogram, okay, and I can see how many counts I'm getting here. Okay, so my max counts is substantial. Okay, so, but remember I have a 65,000 count dynamic range. Okay, so I could safely increase this to maybe 0.5, 0.6, not have a problem. Okay, so I'm going to go ahead and do that. I'm going to increase this. We'll go 0.5. Okay, even if it doesn't look good, there's another adjustment we can make. Okay, so I can see a little more detail now. You can actually see the beam stop here blocking off the direct beam. Okay, so if we want to make this look a little more aesthetically pleasing, if I right-click Image Display, I can change the contrast limits here. Okay, so instead of having a negative contrast limit, I'll just put 0 in there, and then I'm going to increase my max here, or my high. So right now it's only 27. If I put in 100, and you kind of have to play around with this, you can see this kind of evens out a little bit more. Okay, and that looks a little more aesthetically pleasing. So I can increase that some more. If I go 150, right, and that looks a little better still. Okay, so sometimes the digital adjustment that it inherently gives you a nice result. Sometimes it doesn't. Sometimes you have to play around with it. Okay, but I have a diffraction pattern now that's isolated from the substrate. Okay, so if I want to do the same thing for the film, okay, screen goes down. Okay, I'm going to go back into image mode. I turned off diffraction, lift the screen back up. Okay, and now I'm going to increase my exposure time back again so I can see a little bit better. Okay, and now I'm going to shift back over to the film. Okay, so there you can see I could be over the beam stop partially too. It doesn't matter. Okay, it doesn't matter if I'm over the beam stop or not. It's just what's underneath it, which is the film. Okay, so there you can see I'm over the film. Right, so screen goes down, hit the diffraction pattern button. Okay, I would again, I'll take a quick look in here just to see that my pattern is shifted correctly. Okay, and it is. Excuse me, I'm going to sneeze here in a second probably, or maybe not. All right, so anyways, decrease the exposure time back to 0.01, lift the screen up. Okay, and there you can see, now that's very obvious okay, the change that you're seeing. You're also seeing here too, my max counts that I was getting before are a lot less, okay? So it's a textured film. It's not a single crystal though, perfect, like this is, okay? So single crystals inherently are the most likely to cause damage when you're taking the diffraction patterns because they're really well ordered and they make really sharp spots. Okay, so we're seeing spots here, but they're not as sharp. Okay, so one of the things I can do just to demonstrate this, so if I use the multifunction knob, you can see, right, see the pattern shift around? Okay, so see there, and I'm starting to see the direct beam. I don't want that. Okay, you don't want to see the direct beam. Okay, I could probably shift the pattern a little to the left. Yeah, there we go. Okay, again, you want it centered just for aesthetics. Yeah, so right about there, that looks good. Okay, and again, I'm going to do a test exposure. So I'll do 0.1. 0.1 is a good test exposure time. Okay, and then if I can do the same thing, analysis histogram, so I'm only getting to 400 here. Okay, so realistically now, whereas before I was stopping at like half a second, I could probably put in realistically 2 or 3 seconds and not have a problem. And actually I'm going to get probably a very nice looking pattern by doing that. Okay, so I'm going to change this here. We'll put in 3 seconds, and then I'm going to do start acquire. Give this a second here to do its, or 3 seconds I should say. All right, and you can see now that that's very, very aesthetically pleasing. I don't really need to make any digital adjustment, although I can. If I come over here to display control, particularly this gamma adjustment, okay, if I make a gamma adjustment, this makes it easier to see those fainter spots a little bit better. Sometimes you can see the imperfections in the pattern a little bit more, but even with just no gamma adjustment, it looks pretty good. Okay, but I'll increase the gamma here just a little bit. Yeah, right about there. Okay, so you can see those a little bit better. Okay, and so we now have, so this is from the film, that's from the substrate. Okay, so you can see the difference between these really, really readily now. Okay, because we've isolated them again with the selected area aperture. Okay. So the last thing to discuss here, I'm going to go ahead and stop the video, is establishing the orientation between the pattern and the image. Okay, so I'm going to go ahead and retract the camera and put the screen back down, and then we will discuss doing that. So this was my original bright field image. And so we isolated a diffraction pattern from here and from here. And so that was from the substrate, that was from the film. So now the last thing you need to do is you need to establish the proper orientation relationship between the diffraction pattern and the image. Okay, so without going into all the theory behind it, the diffraction pattern is really a look at the reciprocal lattice or reciprocal space of your specimen, okay, or in this case where you're collecting the diffraction pattern from. Okay, and so if you understand the reciprocal real space relationship, you know there is a direction in reciprocal space that is parallel to a direction in real space. Okay, and so that's what we need to establish, is what is the orientation, proper orientation that aligns the parallelism between the diffraction pattern directions and the real space directions. Okay, now I already know this because I've done it. It's called rotation calibration. I'm not going to go through how to do it. Okay, but what I know for this particular instrument, and your particular instrument may be different, on newer instruments you usually don't have to do this, because usually the engineering now is such that there's no need to perform rotation calibration. This is an older instrument though, and we do have to do it. Okay, but if I take this image, okay, or I should say this is the diffraction pattern, if I rotate this, okay, so if I come to, let's see, where is it? Process rotate, and I go counterclockwise, that's important. If I go counterclockwise 93 degrees, okay, so I have 93 degrees here, and again I can readjust my digital contrast limits. Okay, so we'll put that at, I don't know what we had before, I think we had 150. Yeah, right there. Okay. Now I have the necessary parallelism. Okay, so in other words, you can't see it, the direct beam is here, okay, but this direction here in reciprocal space, or in the diffraction pattern, is parallel to this direction, okay, or I should say this direction because we're in the substrate. Okay, so I can do the same thing for this guy as well if I want to know the relationship for the film. Okay, so all I have to do, again, I do rotate counterclockwise, okay, 93 degrees, and so I see now the parallelism here. Okay, let's see if it'll let me, yeah, I can resize it, okay. But this is establishing the correct relationship, okay, between the diffraction pattern and the image, okay. So this is useful now because, without going into, again, all the details, if we look here, I'm going to pull up the silicon one. Okay, this is useful because each of these spots tells us a directionality of a set of crystallographic planes. And so now we can use that to establish that directionality in the actual image, which is very useful, okay, for lots of different applications, crystallographic and otherwise, which I'm not going to get into. Okay, but that's the whole point of doing this, is so that you now have that information available to you. Okay, by indexing this pattern, which again I'm not going to cover, but you can figure out what set of planes corresponds to which set of spots and how those are oriented in the image. Okay. Okay, so I'm going to go ahead and pause for just a second here, and we'll talk about some last remaining aspects of selected area diffraction. So one of the most obvious questions when you're doing selected area diffraction is how big is the area that's contributing to the pattern, and that is quite simply indicated by the projected size of the selected area aperture. So I'm going to shift the, okay, so there you can see, I don't know how big this is. You could measure this really easily. It looks to be, just eyeballing it, it's like a diameter of about 0.75 microns. Okay, so that's what's contributing. Excuse me. Excuse me again. So that's the contributing area to the pattern. Okay, so you have 4 different apertures here at your disposal. Okay, so if I go from 2 to 1, okay, that's the smallest one available. And just ballparking that looks like it's probably, it's sub 200 nanometers, probably like 120, something like that. Okay, that's the smallest one. If I go to number 3, okay, you can see this is substantially larger. Okay, so this is microns in diameter. Okay, but you can see I'm still limiting smaller than I am the area I'm illuminating. But if I go to 4, okay, I'm not actually limiting anything anymore. Okay, this is actually bigger than the beam. You can't see it, but at this point the aperture doesn't help me at all. Okay, so that's a little bit smaller. Again, not small enough to isolate one area from another. This is the one we were using. Okay, so you can imagine if my film was thinner. Okay, so just looking at it right there, the film is about 3/4 of a micron. Okay, but what if the film is thinner this way again? Okay, what if it's thinner than my field limiting aperture diameter? Well, I need to use the smaller aperture then at that point. Okay, and that's why you have aperture 4 here if you're going to do that, or aperture 1 I should say, okay, which is right there. Okay. Another thing to keep in mind, the smaller the aperture you use, the less signal you're going to get in the diffraction pattern itself. Okay, so that's one way. If you're getting too much signal, you can cut down by using a smaller selected area aperture. If you're doing that in the substrate region, like for a single crystal, that usually works really well. If you're doing that in something that is a little more textured, like the film here though, okay, so whoops, where did it go? Oh, we're probably being blocked by the beam stop. Yeah, there we go. Okay, so in other words, if I look at the diffraction pattern, I might see something a little bit different. Okay, let me find it here. That's the image. Okay, find the rotated one. Okay, that's the rotated one for the film. Okay, but if I use a smaller SA aperture, I might see a difference because this film isn't a perfect single crystal. Okay, so if I use a smaller aperture, what's likely going to happen is I'm not going to see quite as much broadening in the spots. Okay, because I'm restricting the number of rains, if you will, or regions, if you will, that's contributing to the pattern. Okay, so I can do that really quickly here. Okay, put the screen down. Go back into diffraction mode. Okay, again, I'm going to shift the camera off here for a second just to take a look. So yeah, the pattern is really faint right now. Again, I've lost a lot of signal. Okay, but I can still see it here. Okay, I can still see it. So again, I'm going to have to use a lot longer than 3 seconds, but I'll do the test exposure here just to see. Right, and I'm getting like nothing. Okay, I'm barely clipping 300 counts. So realistically now, if I multiply that by 10, I should get to 3,000. Okay, so if I go, 3-4 seconds, that should be plenty. In fact, I could probably go 5 and not have an issue. Okay, so my max counts should increase by whatever the factor is. So if I go from 0.1 to 5, my max count should increase by a factor of 50. Okay, so I'll go ahead and do the acquire here. It's going to take 5 seconds. We should see something a little bit better. Okay, and we can go ahead here. We do the analysis histogram. Yeah, so we're still pretty low on the counts, but what I'm going to do here, I'm going to make the digital adjustment. Okay, so we'll put that at 0. We'll increase that. We'll go to 150 just to see if that gives us what we want. All right, so that looks a little bit better. In fact, we probably drop that down just a little bit. Okay, and then we'll do the rotation. So process rotate 93 degrees counterclockwise. And I'm going to have to do the adjustment again. Go 0, 120. Okay, and there you have it. Okay, so now if I compare, this was the pattern I had originally. Okay, with the larger SA aperture on the right. Get them the same size there so you can see. Okay, but you see the difference between these? Okay, the spots here, I see the same spots, but they're way smaller here. Okay, and they're not as diffuse. Okay, again, it's not a perfect single crystal. Okay, but if I isolate less and less of an area, I get closer to that. Okay, if I go down to literally nothing, right, then I in principle I would have focused spots. Okay, so I see less evidence of the imperfections in a smaller area or using a smaller SA aperture than I do here. Okay, so I hope that makes sense. Okay, so then one last thing to consider here. I'm going to go ahead and flip the screen down. go out of diffraction mode. Okay, I'm going to go ahead and minimize these. Okay, so that's my smallest field limiting aperture. So what am I supposed to do then if I want to get a diffraction pattern from an area smaller than that? Well, I have to use what's called convergent beam electron diffraction, or CBED. Okay, so in that case, my limiting size is literally determined by the area that I'm illuminating. Okay, so I'm gonna go ahead and I'll come back here to the viewing screen, flip this down. I'm not gonna go into CBED in a lot of detail here, just kind of as just to start with here, okay? So it's probably a little hard to see. I'm gonna take out my beam stop here though, because we don't need it in anymore. Pull it out, rotate it away. Okay, but you can see that's the area I'm illuminating. I have no SA aperture in. Okay, but if I want to illuminate a really small area, I take my C2 control, my intensity knob here. Okay, and I can make this as small as I want. Okay, and I can literally focus this down depending on the spot size I have. Okay, the higher I go in numerical spot size, the smaller the beam is at crossover. Okay, I could get sub-nanometer, okay, and I can get well below that 120 nanometers that is the smallest field limiting aperture size. Okay, if I do that, again, we already saw this, but right, so I have my beam at crossover here. Okay, if I go into diffraction mode now, okay, you can see, it's probably a little hard to see, but I can see now I have disks, right? I have disks because I have a convergent beam electron diffraction pattern, or a CBED pattern, okay? And so I will do another video covering CBED, how to record CBED patterns and whatnot, what CBED is useful for doing, okay? But that's what you'd have to go to at that point, is you'd have to go to CBED, okay? So this is the conclusion of the demonstration. If you have any questions, please feel free to ask me. If you have any requests for topics you'd like to see covered, please feel free to ask me about those too. Thank you.